The night sky is full of wonders, but nothing quite compares to the secrets hidden within the Virgo Supercluster. Stretching over 100 million light-years, this cosmic neighborhood holds mysteries that defy even our wildest theories. From galaxies that vanish without a trace to baffling signals with no clear origin, the deeper we look, the stranger it gets. Today, we're uncovering 25 of the most mind-bending phenomena lurking in this corner of the universe, each one more puzzling than the last. So buckle up, because what you're about to discover might just change how you see the cosmos forever. One of the biggest puzzles in the Virgo Supercluster isn't something we can see, it's what we can't see. Scientists have spent decades measuring the mass of this colossal cosmic structure, but there's a glaring mismatch. When they tally up all the visible stars, galaxies, and gas, it falls startlingly short of what gravity tells us should be there. So where's the missing mass? The math suggests there's up to 5 times more matter hiding in the shadows than what we've actually spotted. One leading theory points to dark matter, an invisible substance that doesn't emit light or energy but exerts gravitational pull, acting like cosmic scaffolding. Yet despite countless experiments, no one's directly detected it. That's led some researchers to explore radical alternatives, like tweaking the laws of gravity itself. Could Einstein's equations need an update, or is the universe playing a trick on us with matter we simply can't grasp? Either way, this ghostly gap in our calculations remains one of astronomy's most tantalizing unsolved cases. But how do we even know dark matter exists if we can't see it? The answer lies in the way gravity bends the fabric of space itself. When light from distant galaxies travels through the supercluster, it doesn't always move in a straight line. Instead, it warps around unseen mass like a cosmic funhouse mirror. This bizarre bending, called gravitational lensing, reveals the presence of invisible matter tugging at space-time. Some of the sharpest evidence comes from detailed maps of these distorted light paths, showing vast halos of dark matter enveloping galaxy clusters like ghostly fingerprints. Meanwhile, underground labs hunt for dark matter particles directly, using ultra-sensitive detectors buried deep beneath mountains to shield them from interference. Yet decades of searching have turned up nothing conclusive. The particles might be too elusive, or perhaps our models are missing something fundamental. The mystery only deepens when you consider alternate theories, like modified gravity, where the rules of physics themselves behave differently on galactic scales. But with new telescopes and experiments pushing the boundaries of detection, one thing's certain: solving this puzzle could rewrite our understanding of the universe itself. Deep within the Virgo Supercluster lies a cosmic paradox, a vast, yawning emptiness known as the Virgo Void. Picture a bubble stretching over 300 million light-years, where galaxies are eerily scarce, as if the universe forgot to fill this corner of space. Unlike typical voids, which are common in the cosmic web, this one defies expectations. Normally, such empty regions form where gravity hasn't had enough time to pull matter together. But the Virgo Void's sheer size and location, right in the middle of one of the densest superclusters, leaves scientists scratching their heads. What makes this void so peculiar isn't just its emptiness, it's what's happening at its edges. Instead of the usual slow drift of galaxies, observations reveal unusually sharp boundaries, almost like a wall separating this desolate expanse from the bustling cosmic neighborhoods around it. Some researchers speculate that dark energy, the mysterious force accelerating the universe's expansion, might be sculpting these voids faster than gravity can keep up. Others wonder if we're seeing the aftermath of an ancient collision between titanic structures, leaving behind a ghostly imprint. The real puzzle: voids like this shouldn't exist in their current form if our models of cosmic evolution are complete. Simulations struggle to recreate such extreme emptiness without tweaking the rules of physics. Could this be a clue that we're missing a key ingredient in our understanding of the universe's structure? or is the Virgo Void hiding something even stranger in its depths? One thing's certain, this silent abyss holds secrets that could reshape our cosmic blueprint. Nestled among the bustling galaxies of the Virgo Supercluster, there's a cosmic enigma drifting almost unnoticed ultra-diffuse galaxies, or UDG. These ghostly structures look like someone took a normal galaxy and stretched it thin, spreading its stars so sparsely that they barely glow against the blackness of space. Some are as wide as the Milky Way but contain just 1% of its stars, making them nearly transparent. Spotting one is like trying to see a faint wisp of smoke across a foggy night sky. Yet, against all odds, they're thriving in one of the densest regions of the universe. What makes UDGs truly bizarre isn't just their faintness, it's their resilience. Most galaxies this fragile would have been shredded apart long ago by the gravitational tug of war within a supercluster as crowded as Virgo. But these cosmic ghosts cling to existence, drifting undisturbed for billions of years. The secret: astronomers suspect they're packed with staggering amounts of dark matter, so much that its gravitational grip acts like an invisible shield, holding their fragile stars together despite the chaos around them. Others theorize they might be failed galaxies, objects that started forming stars but ran out of gas, literally leaving behind these eerie, half-formed relics. But here's the twist: not all UDGs follow the rules. Some, like the infamous Dragonfly 44, contain almost no dark matter at all, flipping the script on what we thought kept galaxies intact. How do these outliers survive without their invisible armor? The answer might lie in their origins. Perhaps they're the scattered remains of larger galaxies torn apart long ago, or cosmic wanderers ejected from violent collisions. Every new discovery deepens the mystery, proving that in the Virgo Supercluster, even the faintest glimmers can hold the universe's most stubborn secrets. Winding through the Virgo Supercluster like a celestial serpent, the Virgo Stellar stream stretches across the night sky, an eerie river of stars with no galaxy to call home. This vast, ribbon-like structure isn't just a random scattering of stars. It's the cosmic aftermath of a brutal galactic feast. Billions of years ago, a smaller galaxy strayed too close to the supercluster's gravitational giants. Slowly, mercilessly, it was torn apart, its stars strewn across space in a shimmering trail that lingers to this day. What makes this stellar graveyard so fascinating isn't just its tragic origin, it's how perfectly preserved it remains. Unlike messy collisions that scatter debris randomly, the Virgo stream arcs with surprising grace, its stars moving in near-perfect unison. That delicate structure tells astronomers this was no sudden crash, but a drawn-out process called tidal disruption, where the victim galaxy was stretched like taffy over eons. Every star in this stream is a silent witness to the supercluster's cannibalistic past, offering clues about the growth of these cosmic titans. Yet the stream holds even deeper secrets. By tracing the chemical fingerprints of its stars, scientists discovered something unexpected. Many are far older and metal-poor than typical galaxy remnants, suggesting their original home was a primordial dwarf galaxy, one of the universe's first building blocks. That makes this stellar river more than just debris. It's a fossil from the cosmos' infancy, preserved in the supercluster's gravitational amber. And there's a twist: the stream's path doesn't quite match current models of the Virgo Supercluster's gravity. Some invisible force seems to be tugging at it, perhaps an unmapped pocket of dark matter, or evidence of long-forgotten collisions we've yet to piece together. One thing's clear: in this river of lost stars, the universe has left us a breadcrumb trail to its most violent chapters. Among the countless mysteries of the Virgo Supercluster, one stands out as particularly perplexing: the strange behavior of its expansion. While the rest of the universe races outward at an accelerating pace, driven by dark energy's mysterious push, this supercluster seems to resist the trend. Instead of galaxies flying apart, many within Virgo cling together, locked in a gravitational tug of war that defies expectations. The math is clear: dark energy should dominate, overwhelming gravity on the largest scales. Yet when astronomers measure the motions of galaxies here, something's off. Some regions expand too slowly, while others show peculiar flows that can't be explained by visible matter alone. One radical idea suggests our models might be incomplete, that dark energy's influence isn't uniform but patchy, like a cosmic quilt where some areas feel its pull more than others. This inhomogeneous cosmology theory paints a universe far lumpier than we've assumed, with superclusters like Virgo sitting in bubbles where the rules differ subtly. But there's another possibility: hidden structures, vast, unseen walls of dark matter could be warping the supercluster's dynamics, creating gravitational eddies that trap galaxies in place. Or perhaps we're witnessing the aftermath of colossal collisions, where past crashes between galaxy clusters left behind invisible scars that still shape motions today. Each telescope survey brings new layers to the puzzle, proving that even our best cosmic blueprints might need revisions. Whether it's dark energies, quirks, or unseen cosmic architecture, one thing's certain: the Virgo Supercluster isn't playing by the usual rules, and its defiance could rewrite physics as we know it. At the very heart of the Virgo Supercluster, a cosmic titan defies expectations: the supermassive black hole anchoring the galaxy M87. While most black holes scale with the size of their host galaxies, this one breaks the mold. Clocking in at a staggering 6.5 billion solar masses, it's disproportionately massive, as if someone jammed the engine of a galactic cruiser into the frame of a starship. How did it grow so large? The answer might lie in Virgo's violent past. Over billions of years, M87 likely devoured countless smaller galaxies, funneling their black holes into its core like marbles down a drain. Each merger added weight, turning this gravitational monster into something far beyond ordinary. But size isn't even the strangest part. This black hole fires off a colossal jet of plasma stretching 5,000 light-years into space, a cosmic blowtorch blazing at nearly the speed of light. What's bizarre is how eerily straight and stable the jet remains, unlike the chaotic outbursts seen from other supermassive black holes. Some researchers think magnetic fields deep within the accretion disk act like a railgun, focusing the jet into a precision beam. Others speculate the black hole's spin plays a role, acting like a drill bit twisting the outflow into a tight spiral. The jet's structure even flickers in ways we can't yet explain, with knots of material brightening and dimming as if something unseen is tugging at them from within. Here's where it gets weirder. The jet isn't just spewing energy, it's recycling it. Observations suggest some of the expelled material loops back in a vast cosmic conveyor belt, raining down onto the black hole to fuel new eruptions. This self-sustaining cycle challenges our ideas about how black holes evolve, hinting at feedback mechanisms we've barely begun to grasp. And with the Event Horizon telescope now mapping the chaos around M87's event horizon in unprecedented detail, one thing's clear: this overgrown giant isn't just a relic. It's an active laboratory, rewriting the rules of extreme physics right before our eyes. Hidden between the blazing galaxies of the Virgo Supercluster, there's a whisper of light so faint it was almost overlooked: the mysterious glow of intracluster light. This ethereal haze doesn't belong to any single galaxy. Instead, it drifts like cosmic fog in the voids between them, a ghostly remnant of countless stellar farewells. Astronomers believe this glow comes from stars violently ripped from their homes during galactic collisions, left to wander the darkness alone. But here's the puzzle: simulations predict these stars should scatter evenly, filling the gaps like sand settling in a jar. Instead, the light pools in unexpected clumps and tendrils, as if unseen forces are herding them into invisible corrals. Some regions shine far brighter than models suggest, while others remain eerily dark. It's as if the supercluster's history was written in these lost stars, but we're missing entire chapters. One theory points to dark matter's hidden hand. Vast, unmapped halos could be sculpting the light's distribution, their gravitational pull sweeping stars into luminous rivers. Others argue the answer lies in the violence of the past. Recent collisions might have flung stars outward in chaotic bursts, leaving behind uneven trails still too fresh to fade. But the real surprise, some of these orphaned stars appear younger and more metal-rich than expected, hinting they weren't just torn from small galaxies but from massive spirals like our own Milky Way. If true, it means the supercluster's history was even more turbulent than we imagined, with giants shredding each other in clashes we've yet to uncover. Every new observation deepens the mystery. Is Intracluster Light a flawless record of the supercluster's violent past, or are we seeing the fingerprints of physics we don't yet understand? One thing's certain, in these drifting stars, the universe has left us a map. We just have to learn how to read it. Galaxies don't always travel alone, especially the giants of the Virgo Supercluster. According to our best models, massive galaxies like M87 should be surrounded by swarms of smaller dwarf galaxies, like moons orbiting a planet. But when astronomers count these cosmic companions, the numbers don't add up. Theory predicts thousands should be buzzing around the supercluster's heaviest hitters. In reality, we've only spotted a few hundred. This glaring gap, dubbed the missing satellite problem, has haunted astronomers for decades, forcing them to rethink everything from dark matter to the birth of galaxies themselves. The trouble starts with our simulations. When researchers recreate the universe's evolution, dwarf galaxies sprout like weeds around larger structures, remnants of the primordial gas that clumped together after the Big Bang. But out in Virgo, these tiny galaxies are suspiciously scarce. Some might be too faint to detect, hidden in the supercluster's glare. Others could have been torn apart by gravitational forces, their stars scattered into those ghostly streams we see today. But even accounting for these losses, the math still leaves a void where countless dwarfs should be. One leading fix involves tweaking dark matter's recipe. Cold dark matter, the traditional favorite, moves sluggishly, clumping easily into countless small structures. But what if dark matter is warm, moving faster and smearing out those tiny clumps before they can form galaxies? This slight shift could explain why fewer dwarfs survive to the present day. Others suggest supernova might have blasted away the gas needed to fuel star formation in these fledgling galaxies, leaving them dark and invisible. Yet the plot thickens. Recent deep sky surveys have uncovered a new population of ultra-faint dwarfs galaxies, so dim they're practically made of shadow. Could these be the missing satellites lurking just below our detection limits? Or does their sparsity hint at something deeper, like flaws in how we model galaxy formation? The answer might rewrite not just Virgo's story, but our understanding of how all structures emerge from the cosmic dark. Every dwarf galaxy we find, or fail to find, is a clue whispering secrets about the universe's hidden scaffolding. Wrapped around the Virgo supercluster like a scorching cosmic shroud, there's an ocean of gas so hot it defies logic, reaching temperatures of tens of millions of degrees. This isn't just random heat, it's a vast, glowing halo that shouldn't exist in its current form, at least according to our models of how superclusters evolve. Normally, gas this hot is associated with the cores of galaxy clusters, where violent collisions and black hole outbursts pump energy into the surroundings. But here, the heat stretches far beyond those expected boundaries, enveloping galaxies across the entire supercluster in a searing embrace, the real puzzle. The gas isn't evenly distributed. Some regions blaze brighter than others, forming intricate patterns that resemble veins in a celestial body, as if some hidden force is channeling the heat in ways we can't yet explain. One theory suggests the supercluster's turbulent past might be to blame. Over billions of years, countless galaxies have plunged through this space, their motion stirring the gas like a spoon in a boiling cauldron. Collisions between galaxy clusters could have unleashed shockwaves, heating the gas to extreme temperatures and leaving behind this glowing fossil of ancient chaos. Others point to dark matter's gravitational pull, wondering if it's funneling the gas into these strange, uneven distributions. But here's the twist: some of the hottest regions don't line up with any visible galaxies or clusters. There are patches where the gas simmers with no obvious source of energy, like a stove left burning in an empty kitchen. Could this be evidence of long-faded black hole eruptions, their energy lingering long after the engines shut down? Or are we seeing the fingerprints of something entirely new, a process that heats gas without the usual cosmic fireworks? The answers might lie in the gas's chemical makeup. Unlike typical intergalactic material, this halo is laced with heavy elements, ash from generations of supernova and dying stars. That means it isn't primordial. It's been recycled, forged in the hearts of galaxies, and then expelled into the void. Tracing these elements could reveal the supercluster's hidden history, like reading tree rings to uncover a forest's past. With every new observation, this searing enigma deepens. Whether it's rewriting the rules of cluster formation or hinting at unseen forces at work, one thing's clear: the Virgo supercluster's hot gas halo is more than just background radiation. It's a cosmic puzzle burning with questions we're only beginning to ask. Even the most reliable cosmic measuring stick, redshift, isn't as straightforward as we thought in the Virgo supercluster. Normally, redshift tells us how fast galaxies are moving away from us, their light stretched like a cosmic speedometer. But here, some galaxies report conflicting speeds depending on how we measure them, as if the universe can't decide which rules to follow. Take NGC 4569, a spiral galaxy whose redshift measurements disagree by baffling margins. Some instruments show it receding calmly, others suggest it's racing away at inexplicable speeds. This isn't just a case of faulty equipment, it's part of a wider mystery called the redshift anomaly. One possible culprit: unknown physics warping the behavior of light itself. Certain theories propose that exotic particles or hidden dimensions could subtly alter light's journey, skewing our measurements. Others point to massive, unseen structures warping spacetime along our line of sight, bending light in ways that mimic inconsistent velocities. The plot thickens when you connect these quirks to the Hubble tension, another cosmic headache where the universe's expansion rate changes depending on whether we measure it with nearby galaxies or distant starlight. If Virgo's redshift anomalies stem from similar gaps in our understanding, they might hold clues to this bigger puzzle. Yet skeptics argue the answer could be simpler: dust. Virgo's dense neighborhoods are littered with cosmic debris that might scatter light unpredictably, muddying the data. But that doesn't explain why these anomalies cluster in specific regions, as if the supercluster itself has zones where physics gets creative. Whatever the cause, each conflicting measurement is a reminder. Even our most trusted cosmic tools have limits, and the universe loves to surprise us. Solving this riddle could mean refining our instruments or rewriting entire chapters of astrophysics. Tucked away in the Virgo supercluster, there's a cosmic crowd that shouldn't be there, a dense swarm of galaxies known as the Virgo overdensity. Picture a packed subway car in an otherwise empty train. This region defies the universe's usual spacing, cramming far more galaxies into one area than our models predict. What's bizarre isn't just the number of galaxies, it's their motion. Instead of drifting apart with the universe's expansion, they seem tugged toward something massive lurking beyond our line of sight. Some researchers believe this overdensity might be the outermost tendril of the infamous Great Attractor, a gravitational anomaly pulling entire galaxies toward it at millions of miles per hour. The problem: we can't see it directly. Hidden behind the Milky Way's dusty bulge, this mysterious force remains one of astronomy's great blind spots. Yet its influence is undeniable. The Virgo overdensity's galaxies share the same peculiar drift, as if caught in the wake of some invisible cosmic riptide. Not everyone's convinced. Alternative theories suggest we might be seeing the ghostly imprint of a primordial flaw in the universe's structure, a relic from the Big Bang where matter clumped more densely than elsewhere. Or perhaps dark matter's tangled web formed a rare knot here, stitching galaxies together against the pull of expansion. But here's the twist. Recent sky surveys reveal the overdensity isn't just a flat layer. It's sculpted into three-dimensional filaments winding through space like a river of galaxies. That complexity challenges even our best simulations, which struggle to recreate such intricate crowding without breaking known physics. Whether it's a signpost pointing to the great attractor or evidence of deeper cosmic quirks, one thing's clear. This crowded corner of Virgo is forcing us to rethink how structure emerges in the universe. And every new map of its tangled threads brings us closer to decoding the forces that shape existence itself. Galaxies and dark matter go together like gravity and motion, except when they don't. Meet NGC 1052 DF2, a cosmic rebel that seems to defy one of astronomy's most fundamental rules. Unlike nearly every other galaxy we've observed, this one appears to have almost no dark matter at all. It's like finding a car that runs without an engine, so bizarre that some scientists initially dismissed it as a measurement error. First spotted lurking in the Virgo Supercluster's outskirts, DF2 isn't just an oddball. Its stars move sluggishly, their speeds far too slow for a galaxy of its size if dark matter were present. Normally, galaxies rotate so fast they'd fling themselves apart without the gravitational glue of dark matter holding them together. But DF2's stars drift calmly, as if they've been left unsupervised in a cosmic playground. The discovery sent shockwaves through astrophysics. Skeptics argued we might be misreading the data. Perhaps DF2's stars aren't where we think, or hidden gas clouds are skewing the math. Others proposed wilder ideas. Maybe DF2 formed in a freak collision, stripping away its dark matter like a snake shedding skin. There's even a tantalizing clue nearby, a massive elliptical galaxy whose gravitational pull could have ripped away DF2's invisible anchor long ago, leaving behind this eerie, lightweight shell. But here's where it gets really strange. DF2 isn't alone. More dark matter-deficient galaxies have since been found, each one challenging our theories about how galaxies form. If dark matter isn't always the cosmic puppeteer we thought, what else could be shaping these structures? Some researchers wonder if alternative gravity theories might explain their stability, or if we're glimpsing a rare class of galaxies born in unusually quiet cosmic environments where dark matter never got a foothold. Every new observation fuels the debate. Are these galaxies flukes or clues to a universe more varied than we imagined? One thing's certain, in the Virgo Supercluster, even the exceptions are rewriting the rules. Deep within the Virgo Supercluster, an invisible storm rages not of wind or rain, but of raw cosmic energy. Spanning millions of light years, a faint yet colossal radio halo pulses with whispers from the universe's most violent forces. Unlike the crisp radio bursts from black holes or pulsars, this emission is diffuse like static from a forgotten channel, stretching across galaxy clusters with no obvious source. Astronomers first detected this ghostly signal by combining data from dozens of telescopes, revealing a sea of low-frequency radio waves too vast to trace to any single galaxy. The leading theory, turbulent magnetic fields woven through the supercluster like invisible spiderwebs, could be accelerating particles to near light speeds. As these charged particles spiral along magnetic lines, they emit synchrotron radiation, the same process that lights up auroras on Earth, but on a cosmic scale. Yet there's another possibility. These radio waves might be relics of ancient cataclysms. When galaxy clusters collide, they unleash shockwaves powerful enough to fling electrons across space like cosmic shrapnel. Over eons, these particles lose energy but keep glowing faintly in radio wavelengths, a fading echo of collisions that shaped the supercluster billions of years ago. Some patches of the halo even align with known crash sites, like scars left by gravitational violence. But here's the twist: not all the emission fits this story. Certain regions glow brighter than the models predict, hinting at ongoing acceleration we can't yet explain. Could unseen black hole jets or dark matter interactions be pumping energy into the system? Or is the supercluster's magnetic field stranger than we thought, with pockets of extreme turbulence acting as natural particle accelerators? Every new radio map deepens the intrigue. Whether it's a fossil of past chaos or a sign of hidden physics at work, one thing's certain: this invisible halo proves that even the empty spaces between galaxies crackle with secrets, waiting for the right tools and the right questions to reveal them. Deep in the Virgo supercluster, there's a cosmic anomaly that shouldn't exist, a vast stretch of space where quasars, the universe's brightest beacons, are almost nowhere to be found. Dubbed the Quasar Desert, this region defies expectations. Normally, dense superclusters like Virgo should be teeming with these luminous giant supermassive black holes in a feeding frenzy, gobbling up gas and shooting out enough light to outshine entire galaxies. Yet here, they're curiously rare. What's strangest isn't just the lack of quasars, it's why they're missing. One theory points to the supercluster's chaotic environment. Quasars thrive on a steady diet of gas, but Virgo's crowded neighborhoods might be too disruptive. Imagine trying to eat a meal in the middle of a hurricane. Galaxies constantly whizzing past could strip away the gas before black holes get a chance to feast. Others suggest the gas itself might be too hot here, refusing to cool enough to fall into black holes' gravitational clutches. But there's a twist: some quasars do flicker to life in Virgo, only to vanish far sooner than models predict. It's as if something keeps turning off the tap mid-meal. Could supermassive black holes here be starving prematurely, their fuel cut off by colossal galactic winds or outbursts from neighboring black holes? Or does dark matter play a role, somehow stifling the conditions needed to sustain these cosmic fireworks? The mystery deepens when you compare Virgo to other superclusters where quasars blaze with abandon. This desert might hold clues about how black holes evolve in dense cosmic environments, whether they flicker out early or simply never ignite. With new telescopes scanning for faint, hidden quasars, astronomers are piecing together the answer. One thing's certain: in the silence of Virgo's quasar desert, the universe is whispering secrets about black holes' most elusive behaviors. Scattered like sapphires against the velvet darkness of the Virgo supercluster, a rare breed of celestial wanderers catches the eye, stars blazing with an unnatural blue hue, untethered from any galaxy. These aren't your typical stellar residents. Most stars live out their lives in the orderly neighborhoods of galaxies, but these blue strays roam the cosmic wilds alone, glowing with a brilliance that defies their isolation. What makes them so extraordinary? Their color is the first clue. Blue stars are typically young, massive, and short-lived, cosmic firecrackers that burn bright and fast. They shouldn't survive long enough to drift far from their birthplace, yet here they are, strewn across the voids between galaxies as if flung by some unseen hand. One explanation points to runaway stars, objects catapulted from their homes by violent events. Picture a binary star system where one member explodes as a supernova, launching its companion outward like a slingshot. Or perhaps close encounters with supermassive black holes hurl stars into the abyss at dizzying speeds. But there's another, stranger possibility. These stars might be the last survivors of failed dwarf galaxies. When tiny galaxies venture too close to the supercluster's giants, their delicate structures can be shredded by tidal forces, leaving behind only scattered stars. Some of these orphans could retain the blue glow of their original stellar nurseries, outliving their galactic homes by billions of years. The mystery deepens when we study their paths. Unlike the languid drift of typical intergalactic stars, many blue strays move with unexpected speed, tracing trajectories that suggest they're not just drifting, they're escaping. Some even show signs of shock-heated gas trailing behind them, like cosmic exhaust from a high-speed getaway. Yet the real puzzle is their sheer number. Current models predict only a handful of such stars should exist, yet Virgo's surveys keep finding more. Are we underestimating the chaos of galactic collisions, or could some of these stars be forming in situ, sparked to life in the rare pockets of gas drifting between galaxies? Every new discovery challenges our assumptions, proving that even in the quietest corners of the cosmos, the universe has a flair for the dramatic. These blue strays aren't just celestial oddities, they're clues to the supercluster's untold history of violence, ejection, and survival against the odds. Amid the swirling mysteries of the Virgo Supercluster, there's a chill in the cosmic background, a peculiar cold spot etched into the fabric of space itself. This faint but unmistakable dip in temperature, detected in the cosmic microwave background radiation, is like a fingerprint left by something vast and unseen. At first glance, it resembles the infamous cold spot found elsewhere in the universe, but Virgo's version comes with its own set of riddles. Cold spots aren't entirely unusual. The cosmos is dotted with tiny fluctuations in temperature, echoes of the universe's fiery infancy. But this one is different. It's larger and colder than standard models predict, as if a cosmic freezer door swung open in this patch of sky. One explanation points to supervoids, enormous, mostly empty regions of space where the lack of matter causes light to lose energy as it traverses the void, creating a cold imprint in the background radiation. Yet when astronomers scanned the Virgo cold spot's location, they found something puzzling. While there is a void here, it's not nearly big enough to account for the temperature drop. The numbers just don't add up. That discrepancy has sparked wilder theories. Some researchers propose we might be seeing the gravitational shadow of a parallel universe, a bruise left by a neighboring cosmos brushing against our own in the multiverse. It's a breathtaking idea, suggesting that this cold spot could be a window into realms beyond our own. Others argue for less exotic but equally fascinating physics, like primordial ripples in space-time from the Big Bang itself, frozen into the universe's structure like cosmic scars. But the debate is far from settled. Skeptics point to more mundane possibilities: instrumental noise, statistical flukes, or even light scattered by intervening dust. Yet with each new observation, the anomaly holds firm, defying easy dismissal. Whether it's a fingerprint of the multiverse, a flaw in our understanding of voids, or something entirely unexpected, one thing is clear. This chilly enigma is forcing us to question what we know about the universe's deepest layers and what might lie beyond. Galaxies usually spin like tops tossed into space, each one twirling in its own random direction. But in the Virgo Supercluster, something strange is happening. Astronomers have noticed that many galaxies here aren't spinning chaotically. Their axes of rotation align in eerily similar ways, as if some unseen hand is gently nudging them into formation. This bizarre cosmic choreography shouldn't happen by chance. In most of the universe, galaxy spins are scattered like dice rolls, their orientations dictated by local turbulence during their formation. But in Virgo, entire groups of galaxies seem to point in the same general direction, their spins locked into a subtle, large-scale pattern. One leading theory points to dark matter's hidden architecture, vast, thread-like filaments weaving through the supercluster like cosmic puppet strings. As galaxies form along these invisible tendrils, their spins might naturally follow the flow, aligning with the scaffolding that birthed them. But there's another, even more profound possibility. These alignments could be relics from the universe's birth. In the first moments after the Big Bang, primordial gravitational waves or quantum fluctuations might have imprinted these preferred spin directions like grooves in a cosmic record. If true, these spinning galaxies aren't just neighbors, they're witnesses to the universe's earliest moments, their rotations preserving whispers from a time before stars. Not everyone's convinced, though. Skeptics argue that galaxy interactions or mergers could nudge spins into temporary alignment. Yet the scale of this phenomenon, spanning millions of light years, suggests something far grander at work. With advanced simulations and deeper surveys, astronomers are closing in on the answer. Whether it's dark matter's subtle guidance or echoes of creation itself, this spin mystery reminds us, even in the quietest motions of galaxies, the universe hides its deepest secrets. Floating between the galaxies of the Virgo Supercluster, there should be an immense reservoir of gas-invisible fuel for future stars and galaxies. Simulations consistently predicted vast clouds of hydrogen and helium, leftovers from the universe's birth, drifting in the cosmic void. But when astronomers point their telescopes, they find far less gas than expected. It's as if someone siphoned off the supercluster's interstellar fuel supply, leaving behind a mystery with no clear culprit. One leading suspect, supermassive black holes and their explosive tantrums. At the heart of many Virgo galaxies, these monsters lurk, feasting on surrounding material. But they don't just eat quietly. When they gorge on too much gas, they blast out colossal winds and jets, a process called AGN feedback, short for active galactic nucleus feedback. Think of it like a cosmic pressure valve. Gas rushes in, and the black hole violently expels excess energy, heating up and dispersing the surrounding gas so thoroughly it can't cool down and form new stars. Yet AGN feedback might not be the whole story. Some regions of Virgo lack gas even where black holes are quiet. Could other forces be at work? One possibility is ram pressure stripping, where galaxies moving at high speeds through the supercluster's dense environment have their gas ripped away, like a leafy branch stripped bare in a hurricane. Others suggest the gas might have simply been used up, converted into stars over billions of years faster than predicted. Here's the twist: faint traces of gas do linger, but in unexpected forms. Ultraviolet telescopes have spotted wispy filaments of superheated gas, too diffuse to detect with traditional instruments. Some could be remnants of ancient AGN eruptions, while others might be the stretched-out debris of past galactic collisions. The missing gas isn't just a bookkeeping error, it's a vital clue to how superclusters evolve. If too much gas vanishes too soon, galaxies could starve, halting star formation prematurely. Solving this cosmic heist isn't just about finding the missing fuel. It's about understanding whether Virgo's future will be one of brilliant rebirth or quiet exhaustion. And with every new observation, we're piecing together the fate of this colossal cosmic engine. Tucked away in the Virgo Supercluster, tiny galaxies are breaking one of astronomy's fundamental rules, spinning faster than they should. These unassuming dwarf galaxies, often no larger than 1,000th of the Milky Way, are caught in a cosmic balancing act. According to gravity's playbook, their rotation speed should match their visible stars and gas. But when astronomers clock their spins, the numbers scream defiance. These galaxies are whirling so fast they should have torn themselves apart long ago. The Milky Way's own satellite dwarfs obey the expected pattern. Their sluggish rotations line up neatly with their modest stellar populations, but Virgo's dwarfs. They're spinning like frenzied tops with velocities that demand unseen mass anchoring them together. The obvious suspect, dark matter, those invisible halos thought to cradle galaxies like cosmic scaffolding. Yet here's the catch: some of these speedsters show too little dark matter to explain their reckless rotations, while others seem burdened with too much. It's as if the universe handed them identical blueprints, then let each one build itself by a different set of rules. One clue might lie in their brutal environment. Unlike the Milky Way's peaceful outskirts, Virgo's dwarfs endure a gravitational gauntlet jostled by passing galaxies, stripped by tidal forces, even squeezed by the supercluster's searing gas. Some could have had their dark matter ripped away, leaving their stars whipping around like untethered carnival rides. Others might have been drenched in fresh gas during collisions, revving up their spins unexpectedly. But the oddest outliers are the ultra-faint dwarfs, dim, ancient galaxies where stars barely cling to existence. Despite their feeble glow, many rotate stubbornly fast, as if hoarding secrets from the universe's dawn. Could their spins be fossils from a time before dark matter dominated? Or are we seeing the ghosts of long-dead star factories, their motions preserving echoes of a more chaotic past? With every new observation, the crisis deepens. Whether it's flaws in our dark matter models or hidden environmental quirks, one thing's clear. These tiny galaxies are proving that even the smallest players can upend our cosmic expectations. Their rebellious spins aren't just curiosities, they're urgent memos from the universe reminding us how much we've yet to learn. Stroll through the Virgo Supercluster with a cosmic chemist's eye, and you'll stumble upon a puzzling pattern. Heavy elements like iron, oxygen, and neon aren't scattered evenly. Instead, their concentrations rise and fall like a roller coaster, with some galaxies swimming in metallic riches while their neighbors starve. This bizarre metallicity gradient isn't just a quirk, it's a ledger of the supercluster's turbulent life story, written in the language of stardust. The mystery starts with how these elements are forged. Heavy metals aren't born with the universe, they're cooked up in stellar furnaces, blasted into space by supernova or stellar winds, then recycled into new generations of stars. In a well-mixed cosmic neighborhood, you'd expect this stardust to spread relatively evenly. But Virgo's chemistry is anything but uniform. Some outer galaxies boast metal levels rivaling the supercluster's crowded core, while pockets near the center inexplicably lack these expected riches. One clue lies in Virgo's history of collisions. When galaxies merge, they don't just swap stars, they pool their elemental ingredients. Yet simulations show this mixing should create smoother gradients than we observe. Instead, the patchiness suggests something disrupted the process. Perhaps bursts of star formation that burned through gas too quickly, or massive black hole eruptions that ejected metal-rich material into intergalactic space before it could settle. But there's a twist. The most metal-poor regions often coincide with areas where galaxies are unusually isolated, as if they've been cut off from the supercluster's chemical supply chain. Could cosmic highways of gas and dark matter be clogged or rerouted here, leaving these galaxies stranded in elemental deserts? Or are we seeing the aftermath of ancient galactic winds, where fierce radiation from early stars blew precious metals into the void? The answers might rewrite how we understand cosmic evolution. If heavy elements aren't circulating as predicted, entire galaxies could evolve differently, some thriving on recycled stardust, others stunted by scarcity. With next-generation telescopes now mapping Virgo's elemental fingerprints in exquisite detail, we're closer than ever to decoding this chemical enigma. Because in the end, these uneven gradients aren't just quirks, they're cosmic breadcrumbs, leading us through the supercluster's unspoken history of boom, bust, and celestial alchemy. Lurking in the heart of the Virgo supercluster, an invisible glow pulses with the violence of the cosmos' gamma rays, the universe's highest energy light, pouring out in amounts that defy straightforward explanation. This unexplained excess doesn't match any known astrophysical source, flickering like a cosmic beacon with no clear origin. Astronomers first spotted it as a faint but persistent hum in gamma-ray telescopes, a signal too diffuse to come from a single object, yet too intense to dismiss as background noise. So what's pumping out these relentless photons? One tantalizing theory points to dark matter's grand finale, the annihilation of invisible particles colliding after drifting through space for billions of years. According to this idea, when certain types of dark matter particles meet, they could annihilate in bursts of energy, leaving behind gamma rays as their final signature. The Virgo Supercluster, packed with dark matter, would be the perfect stage for this elusive performance, but not everyone sold on the dark matter explanation. Skeptics argue the signal might stem from something more mundane yet equally bizarre. Hidden pulsars, the spinning corpses of dead stars, could be lurking in greater numbers than expected, their intense magnetic fields accelerating particles to near light speeds and firing off gamma rays like celestial lighthouses. Or perhaps unresolved blazars, supermassive black holes spearing Earth with their relativistic jets, are contributing to the glow in ways current telescopes can't disentangle. Here's where it gets even stranger. The gamma rays aren't evenly distributed. They cluster in specific regions, particularly around the supercluster's densest galaxy clusters. If dark matter is the culprit, this pattern suggests it's clumping in ways our models don't predict. But if pulsars are responsible, why do they favor these areas? Could they be relics of ancient star-forming frenzy, left behind when galaxies were younger and more violent? New observatories are now tuning into this gamma-ray whisper, searching for finer details that might crack the case. Whether it's the death throes of dark matter or a cosmic chorus of overlooked pulsars, one thing's certain: this excess isn't just noise, it's a coded message from the supercluster's hidden depths, waiting for us to decipher its origin. And the answer could rewrite everything we know about the universe's most enigmatic forces. Amid the sprawling galaxies of the Virgo Supercluster, there's a class of cosmic oddballs that defy simple categorization: ultra-compact dwarfs, or UC. These tiny, shimmering objects pack hundreds of millions of stars into a space barely larger than a globular cluster, creating stellar densities so extreme they blur the line between galaxy and star swarm. At first glance, UCDs resemble overgrown globular clusters, tight-knit families of ancient stars orbiting larger galaxies. But look closer and the differences emerge. Their stars move faster, their masses are higher, and some even harbor supermassive black holes at their cores, features unheard of in ordinary clusters. This has led to a fiery debate. Are these objects the stripped-down corpses of once larger galaxies, or an entirely new class of cosmic structure? The stripped nucleus theory has gained traction. Imagine a small galaxy venturing too close to a supercluster giant. Over eons, its outer stars are peeled away by gravitational tides, leaving behind only its dense, star-packed core, a celestial peach pit tossed into the void. Observations support this. Several UCDs sit eerily close to massive galaxies, their positions hinting at violent past encounters. Yet not all UCDs fit this mold. Some float in isolation, far from any galaxy that could have shredded them. Others show chemical fingerprints unlike typical galactic cores, more pristine, less polluted by generations of supernova. Could these instead be primordial relics, objects that formed dense from the start during the universe's chaotic youth? The plot thickens with the discovery of UCDs housing black holes rivaling those in full-sized galaxies. This shouldn't happen if they're merely swollen star clusters. Black holes that massive require a galactic-scale origin. One leading UCD in Virgo, M60 Vega 1, weighs in at nearly 200 million solar masses, with a central black hole 10 times heftier than expected for its size. What makes these cosmic crumbs so fascinating isn't just their identity crisis, it's what they reveal about galactic evolution. If most are stripped nuclei, they're fossil records of cannibalized dwarfs, mapping the supercluster's growth through destruction. But if some represent a distinct breed, they could rewrite how we define galaxies altogether. With every new UCD catalogued in Virgo, the puzzle grows richer, proving that even the universe's smallest wonders can upend our grandest theories. For now, ultra-compact dwarfs remain tantalizing enigmas, their true nature hidden behind layers of starlight. Whether they're galactic ghosts or cosmic anomalies, one thing's certain: These tiny titans hold big secrets about how the universe builds and destroys its stellar cities. Galaxies aren't supposed to move like this. Across the Virgo Supercluster, astronomers have detected something unsettling: an eerie, coordinated drift of galaxies toward a seemingly empty patch of space. Dubbed the dark flow, this motion defies the universe's usual expansion, as if countless galaxies are being pulled by an invisible hand. The first clue came from subtle distortions in the cosmic microwave background, the afterglow of the Big Bang. Hotspots in this ancient light appear ever so slightly stretched, as though something massive beyond our observable horizon is tugging matter toward it. Follow-up studies tracking galaxy clusters confirmed the anomaly. Entire swaths of the supercluster are streaming in the same direction at staggering speeds, some exceeding 2 million miles per hour. Skeptics argue it might be a statistical fluke or an artifact of incomplete data. But the scale is hard to ignore. The flow spans billions of light years, suggesting the culprit isn't just a hidden supercluster, but something far more immense. One controversial theory points to a supervoid, an unfathomably vast region of nothingness, whose gravitational repulsion could be pushing galaxies away like a cosmic tide. Others whisper about an exotic gravitational pull from another universe, a radical idea that lingers at the edge of credible physics. Yet the simplest explanation remains the most haunting. We might be seeing the fingerprints of matter so distant, its light hasn't had time to reach us. If true, the dark flow could be our first glimpse of structures beyond the cosmic horizon, their gravity bending the universe in ways we're only beginning to measure. Not everyone's convinced. Some researchers propose the flow could stem from overlooked local forces like the combined pull of known superclusters acting in concert. Others suggest peculiarities in how we measure galaxy motions might be skewing the results. But with each new survey, the signal persists, a siren call from the cosmos' uncharted depths. Whether it's a flaw in our models or a window into the unimaginable, one thing is certain. The dark flow reminds us that even the grandest structures we see might just be ripples in something far greater, a universe still full of secrets waiting to pull us deeper. Drifting like lost embers in the cosmic dark, the Virgo Supercluster holds a peculiar kind of celestial ghost, lonely stars whose final breaths glow with eerie beauty. These aren't your typical planetary nebulae, the radiant shells often seen nestled within galaxies. Instead, they float untethered in the voids between galaxies, their delicate rings and spirals shining where no star should logically die alone. The mystery isn't just their isolation, it's their sheer numbers. Planetary nebulae form when aging stars shed their outer layers, leaving behind glowing husks illuminated by their dying cores. Normally, we'd expect these remnants to stay close to their galactic homes. But here, they're scattered like confetti across the supercluster's emptiest reaches. Where did these stars come from? The leading theory is as violent as it is poetic: galactic eviction. When galaxies collide or brush past one another, the gravitational chaos can fling stars into the abyss like stones from a slingshot. These exiled stars live out their lives in solitude before finally erupting into nebulae, marking their graves far from the stellar cities that birthed them. But there's a twist. Some of these nebulae are too abundant, their chemical compositions revealing they weren't just castaways. They might be relics of entire galaxies torn apart long ago. Their patterns of motion suggest they were once part of dwarf galaxies devoured by the supercluster's giants, their stars now wandering as a cosmic diaspora. Others show pristine, almost primordial elements, hinting they formed in the sparse outskirts of galaxies before drifting free. The real surprise: these glowing ghosts might be tracing the supercluster's hidden architecture. Their distribution doesn't match random scattering. Instead, they cluster along faint filaments, as if drawn by invisible tendrils of dark matter. By mapping their positions, astronomers are uncovering the secret highways along which galaxies exchange stars, gas, and even their very identity. So the next time you gaze at a planetary nebula's delicate glow, remember, in the Virgo Supercluster, even a star's death can illuminate the universe's untold stories of collision, exile, and rebirth. These solitary beacons aren't just pretty relics, they're clues to the supercluster's stormy past, written in light and gas. In the vast cosmic ballet of the Virgo Supercluster, even time itself seems to dance to an unfamiliar rhythm. Astronomers have stumbled upon a baffling quirk, anomalies in the way supernova flicker and fade across this sprawling region. These stellar explosions, nature's most precise cosmic clocks, aren't behaving as expected. Some stretch their light curves longer than relativity predicts, as if time itself were slowing down in pockets of the supercluster. The strangeness centers on Type Ia supernova, stellar detonations so uniform they're called standard candles for measuring cosmic distances. Yet in Virgo, their light curves linger just a little too long, their brilliance dimming at a delayed pace. At first, scientists suspected simple measurement errors. But the pattern persists. These supernovae appear to experience time differently depending on where they erupt in the supercluster. Einstein's theory of relativity offers one possible explanation. Massive objects warp spacetime, slowing time in their vicinity. Virgo's dense galaxy clusters could be creating gravitational wells deep enough to stretch these light curves like taffy. But here's the catch: the anomalies don't always align with visible mass. Some occur in regions too sparse to account for the time distortion, hinting at unseen forces at play. Could dark matter's uneven distribution be amplifying these effects, creating invisible pockets where time crawls? Or might we be glimpsing subtle cracks in relativity itself, evidence that gravity's rules bend differently on supercluster scales? A handful of theorists even float wilder ideas, like exotic energy fields or primordial spacetime defects left over from the Big Bang. Yet skeptics counter with simpler theories. Intergalactic dust might be dimming supernova unevenly, tricking our instruments into perceiving stretched light curves. Or perhaps Virgo's turbulent environment alters how these stars explode, subtly changing their decay rates. As telescopes gather more data, one thing's clear: these time-stretched supernovae are more than curiosities. They're cosmic stopwatches ticking at the wrong speed, and deciphering why could redefine how we measure the universe itself. Whether it's hidden mass, new physics, or something stranger still, Virgo's time anomalies remind us that even the most reliable cosmic rules might need a second glance. Among the towering mysteries of the Virgo supercluster, some of the most profound questions can't be answered by gravity alone. When galaxies spin too fast, black holes defy expectations, or time itself seems to stutter, we might be catching glimpses of a deeper truth, one where quantum physics and gravity finally unite. For decades, scientists have struggled to reconcile Einstein's theory of gravity with the bizarre rules of the quantum world. But Virgo's anomalies could be the testing ground we've been waiting for. Take loop quantum gravity, for instance, a theory where spacetime isn't smooth and continuous, but woven from tiny, indivisible threads. If true, these microscopic knots might subtly alter how gravity behaves on cosmic scales. In Virgo's densest regions, where galaxies cluster like bees around a hive, such quantum tweaks could explain why our traditional math keeps coming up short. Then there's string theory, which suggests the universe hums with hidden dimensions, curled up so tightly we've yet to detect them. If these extra dimensions exist, they might warp gravity in unexpected ways, especially around supermassive black holes like M87s. Its monstrous jets, which stay eerily stable over vast distances, could be tracing the contours of unseen geometry like ripples revealing the shape of a pond we didn't know was there. But here's what makes Virgo special. It's not just one anomaly, but dozens, each one a potential clue. The supercluster's uneven expansion, its rogue galaxies spinning too fast, even its gamma-ray whispers, all could be threads in the same tapestry. Quantum gravity theories predict subtle deviations from Einstein's relativity, and Virgo's extremes might amplify those deviations just enough for us to spot them. Not everyone's convinced, of course. Critics argue these ideas are still untested beautiful math waiting for proof. Yet as telescopes peer deeper, they're spotting quirks that classic physics can't easily dismiss. Whether it's the way dark matter clumps or how light bends around voids, every inconsistency nudges us closer to a breakthrough. One thing's certain, the Virgo Supercluster isn't just a collection of galaxies, it's a laboratory. And if quantum gravity leaves fingerprints anywhere, they're likely hidden in these cosmic anomalies, waiting for us to piece together the universe's most elusive puzzle. As we wrap up this journey through the Virgo Supercluster's strangest enigmas, there's one crucial distinction to make, because not all mysteries are created equal. Some cosmic puzzles come with promising leads, while others leave scientists staring blankly at their whiteboards. Take dark matter, for instance. Even though we haven't directly detected it, we've got compelling evidence: gravitational lensing, galaxy rotations, even the way clusters move. It's an unsolved case, but the clues point toward a tangible answer. Compare that to something like the Virgo Void's razor-sharp edges, or those rogue galaxies spinning too fast without dark matter. These aren't just unsolved, they're unexplained phenomena that defy even our most creative theories. The difference comes down to scaffolding. Unsolved mysteries have frameworks, equations half-filled, experiments underway, like hunting for dark matter particles in underground labs. Unexplained phenomena, though, those are the cosmic curveballs that make researchers question their textbooks. Why does time seem to stutter around certain supernovae? What's sculpting those eerie stellar streams with such precision? These aren't just gaps in data, they're gaps in our very understanding of physics. And that's what makes the Virgo Supercluster so thrilling. It's not just a catalog of what we don't know, it's a living laboratory where every anomaly teaches us something new. Whether it's a problem we're closing in on or a riddle that still leaves us speechless, one thing's certain: the universe loves keeping us on our toes. And who knows, the next breakthrough might come from the most unexpected corner of this cosmic puzzle. From vanishing galaxies to rogue black holes, time-bending supernova to ghostly dark matter, the Virgo Supercluster has taken us on a tour of the universe's strangest backstage secrets. These 25 mysteries aren't just cosmic oddities, they're urgent memos from the universe, challenging everything we thought we knew. The missing satellites, the phantom gamma rays, the inexplicable spins of dwarf galaxies, they all point to one undeniable truth: our cosmic playbook is still missing whole chapters. But here's the beautiful part: every unanswered question is an invitation. Each time a galaxy defies gravity or a void refuses to fit our models, the universe is handing us a new puzzle to solve. And with next-generation telescopes, AI-powered simulations, and bold new theories, we're closer than ever to cracking these codes. Maybe dark matter will finally show its face. Maybe quantum gravity will snap into focus. Or maybe, just maybe, the next big discovery will come from something we haven't even thought to look for yet. So keep wondering, keep questioning, and keep looking up. Because the Virgo Supercluster isn't just a place, it's a promise. A promise that no matter how much we learn, the universe will always have another secret waiting just beyond the light. And who knows, the next revelation might be the one that changes everything. Until then, stay curious. The cosmos sure isn't done surprising.